Today we are going to solve 23rd problem in 30-day lead coding challenge. The problem is bitwise end of numbers range. Let me open the problem. Given a range m n where 0 m and n will be greater than m and m will be at least 0 and at most it can be this value, which is basically maximum value that integer can hold. Return the bitwise end of all numbers in this range inclusive. Well, 5 and 7, output is 4. Bitwise end of all numbers. Well, bitwise end means if we represent the numbers in binary form, like say for example 5 can be represented as 1 0 1 because 5 is this, and 6 is 1 1 0, and 7 is 1 1 1. And if we perform the bitwise end, then what happens is that we have some general rule. If we do end of the same end with 1, then only one, if there is 1 it will be 1, otherwise whatever operation we apply to the binary bit, that means either 0 or whatever, otherwise it will be 0. In every other cases, in every other combination of bit, it will be 0. Either with 0 it will be 0. So only combination of 1 with 1 will become 1. Every other value will become 0. This is the end operation. This is the form of end operation. This is the rule for end operation. So considering this rule, what happens is that for every bit position, the same end operations will be applied. Like in order to calculate the final value of the end operation, suppose this is x, the final actual value will be the end of every digits in its current column. So for this we can see that this is 1, this is 1, and this is 1. So every end operation will lead us to the 1. And here we can see that this is 1, this is 1. So 1 and 1 is 1. Again we will do end with 0, which gives us 0 as the end result. And here we see that this is 1, and the ending with 0 will give us 0, and again end with 1 give us 0. So final result is this, which is in decimal representation 100 is 4. So which is the answer is in example 1. And uh, how we can easily say that this is 4, because there is a binary representation can be easily interpreted like the 0th position, 1 in 0th position is 1, and 1 in 1th position is 2, and 1 in 4th position is 1 in 3rd position is 4. So in this way, if we do the summation of every one entry, we will get the final actual value of actual decimal value of given binary representation. Also, we can say that this is formed by this position multiplied by 2 and this position multiplied by 2 into 2 and this position, which is one value position value, multiplied by 2 into 2 into 2. So which is why this binary representation works. So every representation works in the similar way. Well, if we think about a decimal representation, for 1 2 3, this is binary representation for 1 0 0. So decimal representation for 1 2 3 will be similar way. The first this position value, this is the 0th position, which value will be multiplied with well, there is a simple mistake, which is this position will be multiplied with 1 and this position will be multiplied with 2 and this position will be multiplied with 2 into 2. So final value is 4. So here also first position will be multiplied with 1 and second position will be multiplied with 1 into, we can say, 10, and third position value, which is 1, which will be multiplied with 10 into 10. So 10 is the decimal representation, so which will give us, this is 100 and this is 20 and this is 3. So in this way we get 123. So in similar way binary representation works. Well, let's go with the original problem. Original problem is asking us to find the end of all numbers in the range, and as we can see, we can find the every position's end value, 0th positions, first position, second position, these are independent, and whatever the value we are getting in this position, we will add that value, uh, and whatever value we are getting from first position, we will add that value again, and whatever the value we are getting from another position, we will add that. So finally, position wise, we will calculate the actual value of the bitwise AND operations. So this is what I'm thinking right now. Well, now uh, let's analyze a little bit more about binary numbers. There is a very nice property in binary number. Let's analyze this. Suppose let's say we are writing binary numbers starting from 00 to 8, first 8 numbers. So this is 00 and this is 1. This is first 1 representation. This is representation of 2. This is representation of 3. This is representation of 4. Now let's represent 5. Now let's represent 6. Let's represent 7. Now let's represent 8. Well, there is a very nice property of binary numbers that in the first position that we are interested in calculation of AND operation, we see that the there is a pattern that after every uh, one gap there is a repetition of 0 and 1, 0 and 1, and in second position there are two zeros, two ones, two zeros, two ones. In this way the pattern goes on. And in third position we see that there are four zeros in the beginning, four ones, and again four zeros, again four ones. In this way the pattern goes on. And in fourth position there are eight zeros and again eight ones, eight zeros, eight ones. In this way the pattern will goes on. So if we are concerned about the particular position, what will be the end operation of all other values, all the values in this position, then we need to satisfy that the gap between the numbers should be covered by particular range. Like if we are aiming for the gap 3, here we see gap is 3, and if our block for particular uh, position is not sufficient to to cover that range, like this is the 3 range, and in this position we see that this block of 0 and again block of 1, which are the total block size of 1, continuous 1. So total block size of continuous 1, block size of continuous ones in first position. Let's divide it by position. In 0th position, total blocks of ones will be one size, and in first position total block will be of two size. In third position total block will be of four size, and in fourth position total block will be of 8, which is going like 2 to the powers. It is like for ith position total block size of continuous one will be of 2 to the power I. So if the first number is of 1, if the first number of the particular values contains 1, then if the continuous block size is less than the total size we are interested in, we will never have 0 1 in end operation, because this is of block size 1 and we are interested in covering all the, if we cover all the range with ones, then in that case we will have 1 as a end after performing end operation. Otherwise, if the block is not able to, if the gap is not able to hold that range, like the 0th position, it has maximum continuous of only one values. So if the gap is 3, it cannot hold that range. So eventually this position will not give us the solution. The end operation will not give us 1. So we can simply skip that position, because this position will not give us ones. The only the position give us the value if a gap, like say gap is simply the subtraction of n minus m plus 1, which is the gap. And if gap is greater than 2 to the power I, then this gap, this position, then ith position will always give 0 as end operations. So ith position will always give 0. Say if we apply in this example, we can see that gap here is 7 minus 5 plus 1, which is equal to 3, and 3 is greater than 2 to the power 0, which is 1. 3 is greater than 1, so first position is giving us 0. And similarly, we see that 3 is also greater than 2 to the power 1, which is 2. So this position is also giving us 0 for sure. Now we see that 3 is less than or equals to less than or equals to what? The 4. So next position is block size, continuous block size of 1s will be 4, and this is less than or equals to false. So there is a probability that this position may give 1 as end operation. Now when the probability will be 100%, so we can say that if we have, if m contains 1 in particular position and n also contains 1 in that position, if both of these values contains 1 and the gap is already satisfied. So if this is the case, like gap is satisfied already and both position contains 1 in their position, in that case we will have 1 as a result of AND operation. Well, as we have all the conditions defined already, we can go for the implementation. Now the only things that I would like to clarify that how we will check whether the value in particular position for m and n both are 1 in that particular position. I mean, we have a challenge that checking bit value either 1 or 0 at position I. How will we check that? So what we can do is to, in order to check the bit value in particular position for x, suppose x has representation like 0 0 0 0 1 0 1 0 1 0 0 1 0 1, something like this. And if we are interested in this position, suppose for this position, then if we have some numbers like the numbers in this, after this doesn't matters, after first one. So if we have some number, if we somehow generate this number, so by default the numbers to the left side will be 0, and the if we generate this number and if we do AND operation, then as all the values are 0 both to the left and right side, we can see, so all the values will be 0 in that particular case. So we will be more concerning about the position of this particular value. So what is, if we do AND operation for the numbers like this with x, then if this gives us some value, which is the value is the, which is equals to this one, so if it gives us some value equals this one, then we are sure that the position at this particular position will have uh, does have 1 in that particular position. If it doesn't has 1, then if we perform the AND operation, then this particular position gives us 0 and all other positions are giving us 0 because all other positions already have 0. So if we do AND with any 0, then it will gives us 0, like whether 0 in left side or right side doesn't matter. If we do AND operation with 0, it will give us 0. So if we put 0 over here, then it will by default giving us 0 and to the left side as well, but we have 1 in this position. If so it will only take care if the current particular position has 0 or 1. If it has 0, then it is giving us 0 because 1 will have no value if it is ending with 0, and if it is 1, then it will gives us the solution that checking ith position bit is 1, because if it doesn't has 1, then it won't give us uh, the value. Well, in this way we will be checking the bit position at I is whether 1 or 0. And now how will we generate this value in order to check? So if we want to check at ith position, we have to generate this value. So how we can generate this value? This value is basically equals 2 to the power I. So if we are interested in 0, 1, 2, 3 position, then this is actually 2 to the power I. So we have to generate, we have to have 2 to the power I, and if we end 2 to the power I with x, then this will help us to identify whether the value at current ith position is whether 1 or not. So if we end this and if we have some value, if this gives some value, then we say it has 1 in this position, otherwise we say it has 0 in the particular position. So in this way we will identify. So now in order to generate 2 to the power I, either we can use C++, either we can use 2 to the power I power function. This is one way, and other way is if we do shift operation, then we can also achieve the same thing. Like there is a shift uh, syntax available in C++. So if I want to shift this value to the left side, then what will happen? If I want to shift all the ones in this value, then for 1 times, it will be 0, 0, 1, 0 if I shift for the 1 times. This is 1, and if I shift 1 times, then it will have it will give us this value. If I shift 2 times, then this will give us 0, 1, 0, 0, because 1 is shifted 2 times to the left side. and if I shift for 3 times, then this will give us 1000, which is basically 2 to the power 3, and this is also basically 2 to the power 2, and this is also basically 2 to the power 1, and this is 2 to the power 0. And if we by default, if we put it like this, we are having 0 times shift. So if we do 0 times shift, we will have the same value. Well, so this is another way of generation of this uh, 2 to the power I values in C++. So operation is basically uh, like 1 is basically this representation, and if we want to have something like this, then we have to do, like if we want to have 2 to the power I, then we have to do I times left shift. So this is I times shift, which is same as 2 to the power I, which is same as 2 to the power I, and this 2 to the power I will help us will help us to check the bit value at position I. Well, as we have concluded everything and write down every cases, we can now proceed for the solution. Well, let me start code here. Let's start with answer. Let it be integer is given in the problem. And now if, like, for calculating the answer, if we have end value in particular ith position is 0, then we are not summing up anything. But if we find that particular end in particular ith position is giving us the value is giving us 1 after performing end operations, then we have to do the summation of 2 to the power I for ith position. So 2 to the power I is very much helpful in this scenario. Well, let's start with the left least significant bit towards the uh, most significant bit. We will move towards 0 to uh, 31. So let's start with 0, and now let's calculate the gap. Gap can be calculated outside as well. So let's calculate gap as we defined here. Gap is n minus m minus 1, n minus m plus 1. N is bigger, right? Yeah. Now if we see that this 2 to the power I, which is this range, like the block size as we defined, continuous block size, so which is also 2 to the power I. Let's calculate 2 to the power I first, which can be represented as 2 power I, which is as we defined already. Shift, we have to perform shift operation up to I times. And if we see that, as we mentioned earlier, if the gap is greater than 2 power I, we'll just continue. So this will not give us any answer if gap is greater than 2 to the power I. Otherwise we may have answer only the condition that both of these should be 1. So now let's see uh, bit value uh, for m at position I. Which can be calculated easily by performing AND operation with 2 to the power I. So m and 2 power I. If we do this and if we see that this is giving some value, then we say that this is 1, otherwise 0. So let's define if it has some value, then 1, else 0. Well, we will do the same thing like bit value n at position I, which is also same thing, 2 power I. If we get some value, then it's 1, otherwise 0. Now if both of them are 1, if both of them are 1, then we're gonna calculate answer by summing up the particular value, which is also 2 to the power 1. So 2 to the power I. So 2 to the power I has 3 benefits over here. Now let's return answer. Let's run the code first. Compilation error 16. Well, we forgot to comment out. Let's try with custom tests. And what will be the end operations per 0 to 8. Yes. And what will be the end operation from 5 to 8? This is also same as before. What will be the end operation per 3 and 4. It should give us 2, I guess. 0. 3 and 4. 3 is 1 1. Oh yes. Let's say 4 and 5. 4 and 5. It should give us 4. 4 is 1 0 0. 5 is 1 0 1. Gives 4. Right. Let's say 2 and 3. 2 is 1 0. 3 is 1 1. It should give us 2 now. Yeah. Anyway, let's submit the problem. Runtime error. Integer overflow. Well, let's hold it as a long. Well, there is a problem with this case. Let's do typecasting. Bracket missing. Let's submit. Accepted. There was overflow while calculating gap. Thank you so much for watching this video. Runtime is 8 milliseconds and memory is 6.1 megabyte. Hope you like the video, and if you have any query, please feel free to comment.